Yeah, thank you for reminding me this. And also, I think I missed the other part about the test part. So let me actually show the announcement here. So yeah, as I mentioned, that the test one gonna be available between 11 a.m. to midnight. So which you have 13 hours to work on. So check the Blackboard announcement for the details of each part for the test. Uh, Part one is the online part, which contains the multiple choice problems, and part two contains questions. So you can answer the part two on the Blackboard, or just print a copy and just write the answer using a pencil. So yeah, just check that one. Okay, so let's switch to the topic again. So in general, the computer actually is can be the computer system can be divided into a couple of components: the CPU, and the memory, or sometimes we called RAM, the random access memory. And also we talk about the storage, even though memory is also regarded as a storage, but I just separate these two concepts. The storage I'm mentioning here basically means the hard disk, that you can store the data pretty much permanently. Memory is not really permanent, so that's why these two type of storage, and memory is called volatile storage, and the traditional storage is called the non-volatile, which means once the data is stored in the hard disk, it will actually stay in the hard disk, even though you actually turn off the power and turn the power back on. The data is stored in the hard disk is still going to be there, but the memory is different. And also we're going to talk about I/O. Now, the operating system is just a software, but it's not like any other software, like the software you use to, do your homework, like a Microsoft Office is, like your computer game. Operating system is a special software. Operating system is a software that they used to control and manage the computer hardware, different components. Now, so the module 2, we talk about the processes. All the module 2s are related to the processes. So the processes are basically somehow related to the operations on the CPU. And then module 3, we're going to talk about the memory management. And then we're going to talk about the storage, or sometimes we call the file management, and the I/O management, okay, or I/O system. Okay. So when we talk about the course of operating system, basically discuss each of the component in the operating system that manages the different computer hardware. So in the process, we just talk about when multiple processes are actually sharing the computer CPU, and when the computer actually load multiple processes, and these processes are basically running concurrently. So that means they coexist in the system. Now, in this case, we just talk about how the operating system can manage these multi-programming environment. So that means multiple processes are running concurrently. And so far we have talked about the scheduling, because if multiple processes are actually running the computer system concurrently, then you have to make sure each process going to get the fair share of the computer CPU time, right? You cannot load the process and never actually assign the CPU time. Okay. So now scheduling is very important. We talk about scheduling for the batch system. We talk about scheduling for the interactive systems, and then we talk about the scheduling for the real-time system. So that means the process has some kind of a hard deadline, for each of the CPU burst. Now, today we're going to discuss more about the concurrency. So the process can actually coexist. Process can coexist, and so they share the computer CPU by using various different technique. Okay, now, so when you talk about multiple processes and they share the system, if the multiple processes share the system with multiple CPU, okay, and then we can achieve something called that these processes can execute in parallel. And a system with many CPUs, sometimes people call this kind of system a parallel system. So that means if you have a multiple processes, process 1, 2, 3, 4, 5, and then you have more than 5 processor, more than 5 CPUs, then in this case, life is very simple. You can allocate one process to one CPU, another process to another CPU, another process to another CPU. Now each CPU can execute the process independently, and we achieve something called parallelism. However, so in many cases, we're talking about multiple processes running on a single CPU system. Okay. Now, in this case, there's only one CPU, and then we want to support multiple processes. And we also try to give people some kind of illusion that even though we have a one CPU, but I try to give you illusion that each process is going to be treated fairly. So each actually user may feel like he or she has a dedicated CPU. And the technique we use is called time sharing. Okay. So the concurrency may be achieved by time sharing. Now the difference between parallel and the time sharing is the parallel is a real, a kind of real concurrency. That means these processes actually are executed really in parallel. So they can actually execute at the same time. But the time sharing is different. Even though you have multiple processes and you give the people the feeling that they are running at the same time, but the reality is they're not running at the same time, because the operating system, the scheduler, just basically allocate the CPU to one process at a time. So like the scenario is, one of the scenarios is just like a round robin. So at any particular time, CPU is only executing one process. But because using round robin, you can actually switch, the CPU basically switch among these processes at a very fast speed. And this gives people some illusion that the CPU is actually doing multiple job at the same time. Okay, that's called time sharing. So either way, the concurrent basically means you can support actually multiple processes at the same time. Okay, using these two different approach. Okay, so now when multiple processes are running, now we're gonna eventually experience some kind of situation that these processes requires to use some computer resources, like a printer. or even like a memory space, like a scanner, or like a video camera, or any like a microphone, or many of the different computer devices, computer hardware. So in that case, now you can have as many processes as you want, as far as the computer is powerful enough. You can create 2 processes, 3 processes, 4 processes, 5 processes. And it's hard to say how many processes a system can support. You can support as many as you can, but because there's a hardware limitation, so you cannot support actually. In reality, you cannot support as many as you can, but in practically you can support more and more processes. The only drawback is when you support more processes, and the hardware, the CPU will be shared by more processes. So each process is gonna get less resources. So the performance is gonna suffer. Okay. But you can support many processes. Now, the problem with this is because the hardware is limited. Sometimes we call the hardware resources. For example, the printer is limited. So typically, one computer system, they only attach to one printer. Now, if you have a 3 or 4 processors running, and both process, all these, 2 processors are requested for the printer at the same time. Now, this is going to be the problem, because so you have a scenario that the 2 or more processes try to access hardware resources that are shared among them. Okay, so then we have to deal with that kind of situation. Okay, now the operating system can deal with that situation using some kind of technique called a critical section. Okay, now here's the kind of scenario. So you have a process 1, process 2, process 3. Okay, and then let's say you have process 1, process 2, or process 3. Now process 1 is executing. Okay, now whether they use the concurrent, you use the parallel technique or time sharing, depending on the hardware, the number of CPUs. Okay, now so when process is executing, then process 1 is executing the instructions to perform its task. And now at a certain point, process 1 want to access the hardware. I call the resource 1. That resource could be a computer, a printer, could be scanner, or could be whatever the hardware that attached to the computer system. So the process 1 want to request for the resources. Okay. And then process 2 has its own actually pace, or sometimes called a thread of control. So process 2 gonna execute the instructions one after another. These are each of these are instruction. And then at a certain point, process 2 requests for this resource. Okay. Now, if I only have one resource, instance of resource, like one printer, then if both process 1, process 2 request for the printer, then you got some issue, right? You need to resolve. Now, if I have 2 printer, then it's fine. So you have two instances of the resource. And then you may actually say process 1 can use the printer number 1, the process 2 can use the printer number 2. Okay. Okay. So this is actually one kind of issue. And then process 1, the next couple of instruction, the process 1 going to access the resource 1. And then once the process 1 finish this piece of code, completed actually accessing completed the task of accessing the resource 1, and the process 1 say, oh, I'm done. So, and it's just go back and continue to execute an instruction. And then at a certain point, process 1 gonna say, I need to request for another resource 2. And then process 2 has its own pace. And process 2 may suddenly say, I need to request for resources, right? Now, here's the thing. Once the process 2 request for resource, process 1 request for resource, okay, and the process 1 get the resource, get the printer, whatever the printer the process 1 requested, and then process 1 gonna send the data to the printer, and the printer the job. And then once the process 1's done its job, and the process 1 say, okay, I'm done with the resource 1, so I'm gonna release it. So now resource 2 is free. And then the process 3 can actually grab the resource 2 and do its job. Okay, so this is actually called a shared resource. And this is also shared resources. Now, for shared resources, if at a certain time, when process 1 is requesting for the resource R2, and the process 3 also request for R2 at the same time, and there's only one resource available, instance of resource available. So only one process can get the resource, and the other one which requests for the resource has to wait. Okay, so no, you cannot have one resource and allocate to two different processes at the same time. There's no such a good thing. So in that case, we have an issue. That's called a race problem. Okay, some kind of race problem. So you actually, two processes basically fight for a limited resources. Okay. Now, in modern operating system, we use something called a critical section to deal with the kind of things. Now, what is a critical section? A critical section is a piece of code, a segment of code that cannot be entered by a process while another process is executing a corresponding segment of the code. Okay, so now one of the example of the critical section is a piece of code in here. From here to here, process 1 gonna actually executing to access the resource 2. So that piece of code gonna deal with the resource 2, and this is called a critical section. Okay. Now at the same time, process 3, you gonna have this piece of code in a whole bunch of instruction, and that piece of code is gonna actually deal with the resource 2. So that's the critical section for process 3. Okay. So now, based on the same token, we can say this is also a critical section because this is a piece of code that where the process 1 is going to access resource 1, which is shared, okay, among process 1 and process 2. And then here, this is a piece of code in the process 2 that they're going to deal with the resource 1, and that's the critical section. Okay. So then, we find out for each process, it's basically a piece of code, a whole bunch of instructions. And then we should be able to identify a couple of actually critical section. Now, every time when this segment of code gonna deal with a shared resources, and that segment of code is called a critical section. Okay, so just keep that in mind. What is the definition of the critical section? Now, why the critical section is so important? So why we have to, in this scenario, we have to identify, for each process, we have to identify its critical sections. Because these are a piece of code that may actually collide with the critical section of the other processes. You may actually have some kind of cause some kind of collision with some other process, because that piece of code, the critical section, is a piece of code that access the resources, and that resources actually could be accessed by another process when the other process is actually running its critical section. Okay, so there's a potential that the process 1 and the process 2 could actually collide on the resource 2. Because when process 1 try to enter its critical section and the process 3 try to enter its critical section here, then they're fighting for the resource, and only one process can get the resource. Okay, if you cannot control this, then there might be some problem. Okay, so that means when you design the operating system, you have to design the operating system in a way that you make sure that not two processes can enter its critical section at the same time. Not in this case. Your software, your operating system has to be designed in a way that once the process 1 enter its critical section and the process 2 want to enter the critical section, process 2 cannot and has to wait over here until process 1 finish the critical section, and then process 3 can enter the critical section. So in another word, which means that only one process can enter its critical section, okay, for a particular resource. So any questions on this? Now, we know that we can define a critical section. Okay. Now, how are we gonna do? What kind of activity we should do to prevent such a collision? Okay. So then, in the operating system design, we set up such a requirement for the critical section. Okay, that's called critical section problem. Actually, it's called 4 conditions or 4 requirements. You can, whatever you call it. So any solution to the critical section problem must satisfy the 4 conditions or 4 requirements. Okay. So number one, you have to make sure it's, the mutual exclusion. So if you have a multiple processes, let's say 2 processes, it's running. Okay, this piece of code are going to access the shared variable, shared data resource. Then I define this as a critical section, and this is also a critical section. Now for process 2, this is a critical section, and this is a critical section. And the other code, it's fine. You can do whatever you want. When process 2 is actually running the code in this region, process 1 gonna say, no, fine, it's fine. You never bother me. But when you enter the critical section, then I care about this because I may actually enter the critical section too. So that's the problem. So the critical section problem. Now, what's the conditions we're going to actually set up are, one is guarantee mutual exclusion. So that means only one process may be executing within the critical section. What does that mean? So that means if process 1 is executing its instruction, and the process 1 is currently inside its critical section, okay, then process 2 cannot be in the critical section. Okay, so if process 2 is also running and try to enter the critical section, then the operating system schedule is going to say, no, you cannot do this because process 1 is in the critical section. So you cannot enter the critical section because this mutual exclusion requirement. Okay, so the first condition for the critical section problem is to make sure the mutual exclusion. Okay, now it doesn't matter how many processes you're talking about. If you have another process and you define the critical section here, another critical section here, another critical section here. Okay, so now if this guy is in the critical section, none of the other processes can enter the critical section. Okay, that's number 1. Number 2, prevent lockout. A process not attempting to enter the critical section must not prevent other process from entering the critical section. Now this sounds to be very trivial, right? If process 2 is running at this here, so process 2 is running its instruction, and the process 2 is running the code at this location. So remember that this is not in the critical section. So even in the near future, I'm not going to actually try to enter the critical section because I still have so many instructions to execute. And these instruction is not part of the critical section. So in that case, this process, if this process is not in the critical section, or even not attempt to enter the critical section, so this process cannot prevent other process to enter their critical section. If process 2 is over here and the process 3 want to enter the critical section, process 3 can enter the critical section. Okay, just keep that in mind. Process 2 cannot say, no, you cannot enter the critical section because I don't agree with you. I don't want you to enter the critical section. That's not allowed because the only case the process 2 can say, no, you cannot enter the critical section is the case that when process 2 is in the critical section. If you are not in the critical section, you have no right to reject the other process to enter the critical section. That's basically the rule number 2. Sounds very straightforward, right? The third requirement or third condition is called prevent starvation. A process, like a process 1, or a group of processes, process 1 and process 2, okay, must not be able to repeatedly enter the critical section while other processes are waiting to enter. Okay, now let's say, here's the scenario. If process 3 try to execute and the process 3 is executing the instructions over here, it's almost the beginning of a critical section, right? So the process 3 say, I want to enter the critical section, okay? So then the operating system scheduler actually check the other processes, and the operating system scheduler say, no, you cannot enter your critical section. You cannot, because process 1 is in the critical section. That's okay, right? Because that's basically based on the rule number 1, the mutual exclusion, because process 1 is in the critical section. So the process 3 cannot enter the critical section. And then when process 1 finished the job, quit the critical section. Process 1 is running the code over here. It's done with the critical section. And then the operating schedule process 3 say, can I enter the critical section now? And the scheduler say, well, no, you cannot, because process 2 is currently wants to enter the critical section, and the process 2 should be able to get the resources. So you cannot enter the critical section. So now the process 2 can enter the critical section. Now, based on the mutual exclusion, process 3 is still going to wait. And then when process 2 finishes, and the scheduler say, no, you cannot, because process 1 requested for critical section again. So the process 1 should enter its critical section. So you cannot. Now, you can do this for once or twice. But when you design the operating system scheduler, you cannot just design the scheduler in a way that you actually prevent the 3 to be happening. So that means if process 3 try to enter its critical section, you may actually reject its request because of the mutual exclusion, but you cannot reject the request forever, simply because process 1, process 2 want to actually want to enter the critical section in turn. They want to actually share that resources, and so the process 3 cannot enter the critical section. You cannot design an operating system scheduler that way. Okay, so that kind of scenario is called a starvation. Now, process 3 gonna starve. Okay, process 3 wants to enter the critical section, but the scheduler, the operating system scheduler, never gonna allocate the process 3 to use this critical section. Okay, that's not allowed. Okay, so this is actually requirement 3. A process or group of process must not be able to repeatedly enter the critical section while other processes are waiting to enter. So this is not the case. Okay. You think it probably say, why is there any possibility? Yeah, it's really possible. One of the scenario is when you actually schedule design the scheduler, and you actually prioritize the processes, and the process 3 has to be the lowest priority process. And then every time when process 3 wants to enter the critical section, and the process 1, process 2 always actually get it in and take away the resources and enter their critical section. This way, you're going to prevent the process 3 from entering the critical section forever. That's not a good. Okay. And the number 4 condition. So when you design this critical section solution, you have to make sure these 4 will be satisfied. Okay. Number 4 says, prevent deadlock. Multiple processes trying to enter the critical section at the same time must not block each other indefinitely. Now, how this is going to happen? We can have an example for this case, because sometimes when process 1 need to grab resource 1, resource 2, okay, you need to grab 2 resources and process 2 want to grab a resource 2 and resource 3, and process 3 need to get the resource 1 and resource 2 to enter the critical section. In that case, now you actually eventually end up a kind of scenario that you know that a process 1 requires two resources. The process 1 need a resource 1 and resource 2 to enter the critical section, and the process 3 requires resource 1, resource 2, and to enter the critical section. And now when process 1 try to enter the critical section, and process 1 try to request for resource 1, and the process 1 successfully get the resource 1, but process 1 still cannot continue because process 1 is requesting for resource 2. Now in the meantime, process 3 try to enter the critical section by try to grab the process 1. Now process 2 actually already have the resource 2, and the process 3 is request of resource 1, but resource 1 is currently in the hand of process 1. So now here's the scenario. Process 1 and the process 3 each grab one resource. Process 1 grab a resource 1, process 2 grab a resource 2. And the process 1 request for resource 2, and the process 3 request for resource 1. So now each one grab the resource the other process requires. Now in that case, you get into the situation, it's called a deadlock. Okay, it's called a deadlock. Now the similar example is like if you want to enter a room, and that room has 2 doors. Each door has a key, has a locker, and each door requires to use a key to open the door. And I have one key, and you have the other key. None of us can enter the room because I can open one door but not the other door, and you can open one door but not the other door. So that's called a deadlock. Now, there's a couple of ways to resolve the deadlock, but that's the other story. But when you actually provide any solution using critical section, you have to make sure deadlock should be prevented, should be avoided. Okay. Now that's called the requirements for the critical section problem. Okay. Now let's see, using the critical section, how can we achieve this process concurrency and process, collaboration. Okay. Now, I have 2 processes, 1 and 2. And these processes is running the code. It's just a while loop. Now you can see it's an infinite while loop because while 1, that means 1 basically means true, right? The condition is true. So while 1, that means the while you can always continue to run the while loop. Process 2 is also continue to run the code. So you're going to actually keep doing the loop. Okay. This is actually this is what most of the computer actually systems doing. So when a computer system is actually, when you run some kind of a code like antivirus software, you're basically running the loop infinitely. Each loop you're going to check the network card to see whether I have an email received. So you're going to keep actually running the loop to keep the actual process alive. Now, I can actually achieve this, I can solve the problem allowing only one process to run by using this solution. So in this solution, a process indicates that the interest to enter the critical section by setting the variable C1 or C2 to 1. Okay, now here's the critical section. don't tell me what you try to do, but it's a critical section. That means it's just a block. It's a block of instructions that just try to do something. Okay, and this is also the critical section for process 2. Now these two critical sections may not be the same code. Okay, so this process may actually try to do something. This process may, but these are the critical section for each of the process. Now what I do is I'm gonna add a couple of lines of code before the critical section to control the execution of the critical section. Now, one of the way to control this is using the loop. Okay, here's another loop. Now remember, this while loop is basically, you will find out that this while loop is actually, there's no actually while body for this while loop. Can you see that one? Actually, if you want to actually think about this is pseudocode. It's not Java, or it looks like a Java or a C language, but it's not, because if Java, you should actually put this is the wrong syntax. But anyway, you can interpret this like any code, Python, Java, or whatever. It's a pseudocode. Okay, so now this while loop is a loop that with no body. Okay, so that means, okay, if you want to use Java, then you can put the curly bracket after the while loop. Okay, just say, if this condition is true, then I'm gonna execute the while loop, and then there's nothing to execute. It's now, just keep it in mind, the CS, the critical section, is not in the while loop body. It's after the while loop. Okay. You have any questions on this? Same thing with this side. Okay. So that means when this condition is true, then you're going to execute the while loop, which means you are not going to execute anything, but you stay in the while loop, because the things remember, for the while loop, if you actually write any while loop, and if the condition is true, then you enter the while loop and execute the body, right? And once you complete the execution, and you go back and check the condition, if it's still true, then you continue to execute, and if it's still true, you're going to continue to execute. So if the while loop condition is always true, then you're going to be stuck over here. You're never going to be able to quit the while loop. Okay. Now here you have a while loop, and the body is empty. There's nothing in the while loop body. Now what does that mean? If the condition is true, then this piece of code is going to be stuck over here. Okay. Never going to have a chance to enter the critical section. So because you're going to actually continue to do the while loop if this condition is true. Okay. Now let's see. Similarly, if this condition is true, then process 2 never going to enter the critical section. So in order to enter the critical section, you have to make sure, you have to break that condition. Make sure that condition is not true anymore. Now let's see. In order for the solution to satisfy these 4 requirement condition, now first condition is mutual exclusion. The mutual exclusion says these two process 1, process 2, cannot enter the critical condition at the same time. So if one is in the critical section, the other one cannot be in the critical section, which means if process 1 is in the critical section, then process 2 has to be stuck here. Okay, has to be blocked here, and vice versa. If process 2 is in the critical section, and then process 1 has to be stuck over here, even though process 1 tried to enter the critical section, it cannot, because you have to make sure the condition is true. So you're going to be continue to execute the while loop. You got the point here? Now, how you can guarantee these two processes satisfy the mutual exclusion? Now, C1 and C2 also another actually variable called the well weight. There are three variables. And these three variables are shared variable. What does that mean? You can see that the process 1 can access the variable C1, and also process 2 going to also access the variable C1. So C1 is shared, and the well weight is also shared, and the C2 is also shared. Okay. So here's what happens. Okay. Let's see. So I'm actually into a kind of messy situation. So let's say if process 1 wants to enter the critical section, so then before you process 1 enter the critical section, process 1 going to set the value of C1 to 1. Okay. And also process 1 going to set the well weight to 1. So that means process 1 going to set the value of C1 to 1. And also process 1 going to set the well weight to 1. These two values will be set to 1, right? Okay. Now when process 1 try to enter the critical section, the process 1 need to check the while loop condition. Now, well weight is 1. So that's true, right? Now, what about C2? The value of C2. You don't know, right? Because C2 is not controlled by process 1. C2 is controlled by process 2. Okay. Now what happens? If process 1 try to enter the critical section, so process 1 check the condition. Now well weight is 1 because well weight is set by process 1. Okay. Now C2, I don't know what is C2. Okay. Now if C2 is 1, so well weight is 1, C2 is 1 because if C2 is 1, then process 1 has to wait, right? Because here's 1, that means it's true, and well weight equals 1, that's true. True and true, that means the whole condition is true. If the condition is true, the well weight is going to wait. Now, in which scenario when C2 is 1? In which circumstance when the value of C2 is 1?
I guess like the value of C2 would be 1 when like process 2 wants to enter the critical section.
Okay. Once the process 2 is in the critical section, then the C2 must be 1 because before the process 2 enter the critical section, the process 2 has set the C2 to 1 already, right? So that means C2 is 1, and the well weight equals 1, that's set by itself. Or there's another scenario. So C2 is 1 when actually process 2 also execute the statement here. But right before the process 2 enter its critical section. So in another word, if P1 and P2, in the first scenario, like you said, if C2 is already, process 2 is already in the critical section, that means C2 must be 1 because it must actually execute all these three statements, right? So C critical, it's process 2 in the critical section. So in that case, C2 is 1 and the well weighted is 1. So that means the process 1 has to wait. So that means you have to stuck here. It's just doing the infinite loop until process 2 finish its job, finish the critical section, and then set the C2 to 0. So that means, so when process 1 try to enter, process 1 check the C2 and say, oh, C2 is 1. And the well weight is also 1. Okay, 1 and 1, so I had to wait. And until when process 2 finishes job and finish the critical section part and set the value of C2 to 0. So that means the value of C2 is set to 0. Now, next time, when process 1 continue the loop and checking the condition and check C2 is 1, well weight is 1, C2 is 1, well weight is 1, and suddenly it find out, oh, the value of C2 has been changed. It's 0 now. So that means it's false. Okay, 0 means false. When C2 is 0, that means false. Now, if C2 is false, it's false, and it doesn't matter what is the well weight is 1 or not, whether the second one is true, because this is an end condition. So if there's a false and the truth, then the condition is false. The whole thing is false. So then process 1 going to be able to enter the critical section, right? So that means when process 2 finish the critical section, process 1 going to enter the critical section. Okay. So in that case, C1 and C2 normally should alternate. Okay. However, there's another scenario. What about C1? Process 1 want to enter the critical section. So process 1 execute the C1 equals 1. So now the value of C1 equals 1. And the process 2, in the meantime, also execute C2 equals 1. So both of C1 and C2s are 1. Okay, now next step, the process 1 try to change the value of well weight to 1. And the process 2 want to change the value well weight to 2. Okay, now who will enter the critical section? In this case, both C1 and C2 are 1. But well weight, you don't know, because two processes actually are running the same, try to change the same value well weight. And which one will get this process? Which one will enter the critical section in this case?
Would it be C1?
Will be C1. No, which process will enter the critical section? C1 is a variable.
P1.
P1.
What I meant.
Okay. Are you agree with this? Let me actually just erase all this. Make it clean the space here. So this is a kind of scenario. Okay. Now, so in this case, you remember both C1 and C2 are 1. Okay. Both C1 C2 are 1. You agree, right? Now because C2 is 1, because C2 is actually equals 1 is executed by P2. Now C1 is 1 because C1 equals 1 is executed by P1. Now, who will enter the critical section? Not necessarily P1. You see this? If the well weight is 2, so that means if the value of a well weight is 2, and then 2 compared with 1, that's false. And then here's true and the false. So then P1 will enter the critical section. Not a question. However, if well weight is 1, if where weight is 1, then that means this is 1, and where weight is 1 compared to 1, that's true, right? 1 is equals 1. That's true. So then you have a true and a true, that means that's true. So you're gonna be stuck in a while loop. Now in this case, if where weight is 1, then P2 will enter the critical section, right? Because where weight is 1, 1 compared with 2, that's definitely false. So P2 will enter the critical section. So if you have a situation when both process 1 and process 2 try to enter the critical section, and both process 1 and process 2 set up the value C1 and set up the value of C2 to 1, both C1 and C2 are 1, and then who will enter the critical section is dependent on who actually execute this first. Because if process 1 execute this first, so process 1 change the value of well weighted to 1, and then process 2 actually execute the well weighted equals 2 after P1 set the well weighted to 1. So that means if this statement executed before this statement, then the well weighted can be overwritten by 2, right? So now the well weighted going to be 2. So if this one executed first, this one executed second, then the first one, the well weighted one, will be overwritten by the second assignment. So that means if this one executes first, this one executes the second, then process 1 will enter the critical section, because this one executes first. Now this one executes second, so the well weighted going to be overwritten by this one. So the well weighted going to be 2. So that means whoever actually execute the well weighted assignment first will enter the critical section. Now if this one well weighted equals to process 2 actually execute this well weighted equals 2 first, and then process 1 actually follows this, and the well weighted going to be, the value of a well weighted going to be 1. Whoever actually do the last one going to overwrite the previous value. But the bottom line is the well weight will either be 1 or 2. If it's 1, then process 2 enter first. If the well weight is 2, process 1 enter first, but not both. You agree with this? So this is going to guarantee only one process will enter the critical section. So mutual exclusion will definitely be guaranteed. Okay. Now you see the point why we need another variable called well weight. Simply using C1 and C2 is not enough, because the problem is when process 1 try to set the value of C1 to 1, process 2 set the value C2 to 1, and both are going to actually try to request for entering the critical section, and then both C1 and C2 are 1, then both actually going to be true, so both going to, going to be stuck. Okay, so the well weight basically going to actually allow only one process going to enter the critical section. Any questions on this? Okay, so now we talk about, two processes. So they actually execute, and each process has defined its own critical region, critical section. And then the critical section, solution basically guarantee only one process is going to be able to enter the critical section. No, actually two processes are both in the critical section. That's not allowed. So if they are both allowed to enter the critical section, that means they're both going to allow to access the resource, which is a problem because the resources should not be shared. Okay. Now, one of the classical problem for for the process cooperation is called a producer and consumer problem. Okay. So the producer and the consumer problem is basically simulate some kind of scenario that you have a producer and then you have consumer. The producer gonna produce a product and put the product in the warehouse, and the consumer gonna consume the product from the warehouse, gonna ship the product out of the warehouse, empty the warehouse, so the producer can produce more actual product and put in the warehouse. This is actually used to simulate some kind of producer and consumer problem, okay, which is actually pretty useful, Now here's a typical scenario. There's a shared storage, or you can say it's a memory storage called a buffer. Okay, we call this shared storage a buffer. Now, if you interpret this in producer consumer problem, you can interpret buffer as a warehouse. Okay, a big actual building that house the product. So the producer gonna produce the product and ship into in the warehouse, and the consumer actually ship the product out of the warehouse and sell to the customer. Okay. Now the producer gonna actually has a couple of steps. Now producer gonna actually first produce the data item. Okay. Now producer gonna execute certain of the instruction to produce the product. Okay. And then the next step, the producer gonna place the data into the buffer. Now in the simulation, it's just like a producer gonna actually, once they produce the data and they write the data into the buffer. So they actually copy all this data into the buffer. And then once they actually complete the process and they actually mark buffer as full. Okay, so there's one flag maybe over here. And the flag, when the flag is raised, they say, oh, the buffer is full. Okay, and then the producer gonna produce next item. Okay, so place the data into the buffer and mark the buffer as full, and that's another, instructions. So you have 4 steps, and then it will once they've successfully marked the buffer as a full, and they're gonna produce the producer gonna produce next data item. Okay, once they produce the next data item, they're gonna check the buffer. If the buffer is full, the producer gonna wait. Okay, wait here. It's just actually like doing the continuous loop and wait here until the buffer is empty, and then the producer gonna actually place the data into the buffer again. So now the consumer gonna do the other thing. Now the consumer basically say in this period, the consumer is wait for the buffer to be full. Once the buffer is full, then the consumer gonna remove the data from the buffer. And then the consumer gonna mark the buffer as empty. So they're gonna remove the flag. Okay. Say it's empty, no flag. So then the consumer gonna actually process the data, because that means once they take the data out of buffer, they're gonna actually process data. And once they complete process data, and they're gonna actually go back and wait for buffer full. Wait for next data from the buffer. Now let's see, in this producer consumer problem, what is the critical section for the producer? What is the critical section for the consumer? Which piece of task can be defined as a critical section for producer?
the buffer?
No, critical section is not the shared storage, not the buffer. Critical section is defined as a segment of a code that cannot be entered by process. So the critical section is the piece of code in each of the process that piece of code is going to access the shared data, but critical section is not the shared data itself. So what is the critical section? Is that true? That the critical section is the piece of data that places the data into the buffer, because that piece of code gonna put the data into the buffer, right? Mark the buffer as full. That's also a critical section. So these two defines the critical section. Do you agree? Because produce the data has nothing to do with buffer. It's just actually the process is just do by its own. It's never going to bother the other process. But only when they place the data into the buffer and mark the buffer as a full, that piece is going to impact the other side, the consumer. When producer is place the data into the buffer, the consumer cannot remove the data from the buffer, because during the process of placing data into the buffer, the consumer cannot do this and simultaneously remove the data from the buffer. Okay, so you only allow this piece to be a critical section. Now, what is the critical section for consumer process?
Remove data and mark as empty.
That's the critical section for the consumer. So make sure when producer is actually doing this, consumer should not actually do this. Consumer gonna either in here, or even process the data. That's consumer's its own business. But only when consumer is actually dealing with the buffer, remove the data from the buffer, then you cannot do this while the producer is placing the data into the buffer. Or in the meantime, when the consumer is actually removing the data from buffer, the producer cannot put the data into the buffer. So buffer is shared. Only one process can access it. So each process can define its own critical section. And this is a critical section for producer, and this is a critical section for consumer. Make sense? Okay. So hold on with this. We're going to continue with this on Tuesday. But first, so we have a test on the at 11, start at 11. So, okay. So good luck.
So it opens at 11, but we don't have to start it at 11, right? We can start it whenever.
That's correct. That's correct. Yeah.
But once we start it, we only have an hour to do part 1.
That's correct.
All right, I'm just organizing this because it's a little confusing.
Yeah, I know. Because initially I tried to put everything in on the blackboard, but I realized for some of the problem you need to draw these process and the time. It's not easy to find a software on the blackboard, so that's why I just put the 4 problems separately. But that gave you some advantage, because for part 2 you can do at any time. So you can start at any time, but just make sure you do this part 2 and submit into the on the blackboard before midnight.
Okay, and once we start part 2, there's no time limit for that, right? Just until...
the only time limit is the end of the day. Okay. You have to actually put the problem, the answer back. Okay.
All right. Thank you, Professor. See you on Tuesday.
Yep. Okay. I'll see you later.